Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, Chemical Bonding. Today we begin with lecture 38 from the course, but make sure you watch the previous ones before viewing this one. So in the last lecture, we winded up with a discussion on the molecular orbital theory. And now moving further, in this lecture, we will be talking about back bonding. Well, in the last lecture, what I told you was that we would be discussing about hydrogen bonding, but we will not be discussing that in this lecture. We will be talking about back bonding. And why we are not talking about hydrogen bonding? Because hydrogen bonding is a lecture that we have posted it already in the course on states of matter. And why we have posted it there is because here, even if I would have introduced hydrogen bonding to you, I would not have been able to completely discuss with you people, because there were certain concepts that were required, and the concept was intermolecular forces before you could have a thorough understanding about hydrogen bonding. So after discussing the intermolecular forces in the course on states of matter, we have posted 2 lectures on hydrogen bonding. One is going to be the understanding what is hydrogen bonding, what are the various types of hydrogen bonding, and the next lecture on the applications of hydrogen bonding, which is going to be very important for your competitive examination. So all that we have posted in the course on states of matter. We will be providing the link to hydrogen bonding in the description box below this lecture as well. So now, as far as this lecture is concerned, we talk about back bonding. And back bonding is one of the most important concepts when I talk about JEE Advanced and AIMS. Now, AIMS is no longer going to be an entrance examination separately, but we will be having it in the Neet examination. But at least you can understand, for being the best, you have to understand this topic, right? And I think all of you want to be the top rankers of your examination. All that is required is a thorough understanding of the concept, and then a lot of hard work from your side that is going to make you excel in the examination. So here we are trying our level best to give you this concept in detail so that you have a thorough understanding of the concept, and then you can see even the applications of this concept as it is going to be asked in the examination. So it is going to be essentially a series of about 3 lectures, wherein first lecture, this lecture, we will be talking about what is back bonding. The next lecture, we will be taking up lot many examples of the molecules where we will be seeing back bonding, and then we will be having another lecture where I will be giving you the applications of back bonding, various properties which are going to be influenced because of this back bonding phenomenon. Okay, so let us understand what is back bonding. So what is back bonding? Well, I will not be starting with the definition of back bonding. I will be starting with an example of back bonding. The example, because once you have understood this back bonding concept with one example, it is going to be very easy for you to understand what I have written up in the definition and the other related theoretical concepts related to this concept. It is going to be very simple for you to understand, and we will be starting with the example of BF3. And why BF3? Because BF3 is one molecule that you have been studying from the start of this course, from the time when we learned the Lewis theory. So when we were talking about the Lewis theory, where we learned that the elements, they try to complete their octet in order to acquire stability, we learned that BF3 was one of the important limitations. Why limitations? Because in boron trifluoride, the valence shell of boron, this does not have 8 electrons, it has 6 electrons. So this is an electron deficient compound. Then we learned the valence bond theory, and in the valence bond theory, what we learned was that the shape of the boron trifluoride molecule is a trigonal planar structure where all the 3 boron fluorine bonds, they lie on the equatorial plane in such a way that there is minimum repulsion between the 3 electron pairs, and therefore the angle between the 3 bonds is going to be 120 degree. right? Now all these bonds, they are all equal, but what we learned from the orbital configuration of the atoms is that for boron, in the ground state we have the electronic configuration of 2s2 2p1, but these electrons, they have to be in the half-filled orbitals. The orbitals have to be half-filled so that the overlapping can take place between boron and fluorine. For fluorine, with the electronic configuration of 1s2 2s2 2p5, we have one orbital which is going to be half-filled. This is going to overlap with one of the orbitals of boron, but now the boron orbitals, all of these three have to be half-filled so that we can form three bonds for boron and fluorine, right? So what happens, you all know that one of the electrons from the 2s is going to jump into the 2p so that we get three orbitals which are going to be half-filled. Now these three orbitals, when they are going to overlap with fluorine half-filled orbital, we will be getting the three boron fluorine bonds. But these had to be all equal because the data said so, that these all bonds are equivalent. So that way we learned the concept of hybridization. So these three orbital 1s and 2p, they mix with each other. We get as a result three equivalent orbitals, three orbitals which are equal in shape as well as energy, and these three orbitals we call them as the sp2 hybrid orbitals, right? So these three sp2 hybrid orbitals, they overlap with the 2pz orbital of the fluorine atoms to form the sigma bonds, that is the boron fluorine bonds, which are giving it a trigonal planar structure, right? So I hope all this is clear to you people. So this is the structure that we have. For boron in the center, three boron fluorine bonds pointing at the three corners of a equilateral triangle, right? Now what is not studied so far in the story is about this orbital of boron which is unhybridized and which is empty, right? So this is something that we did not discuss, and now this is going to be the most important thing that we are going to discuss over here, because you can understand that chemical bonding, this takes place so that the molecules, they acquire stability, the atoms, they acquire stability. That is why they are forming the molecules. And boron trifluoride is an electron deficient compound. If in any way we have the boron atoms octet being complete, it will become more stable, right? So now let us understand how this boron trifluoride, boron, is acquiring an octet. Okay, how will it get an octet? It will get an octet because this has one empty orbital which is perpendicular to the equatorial plane. At the same time, if you look at the fluorine atom, fluorine 1,2pz, this has formed a sigma bond over here with the boron atom, right? So there are two orbitals which are completely filled, 2px orbital and 2py, and they are also going to be at 90 degree to the equatorial plane. So one of these is going to be either it is a 2px or a 2py, that is by convention that we take, but it is going to be one of the orbitals which is going to be oriented just like the unhybridized orbital of boron, right? So this two, they are going to be similar in orientation. They are going to be parallel to each other. Now when they are parallel to each other, fluorine has two electrons in this, right? So the lone pair of electrons is present in these orbitals, and this is going to be empty. So empty means that this is a positive charge. It is consisting of a lone pair, it is a negative charge, right? So the negative charge and the positive charge, they are going to attract each other. The lone pair of electrons form fluorine, this is going to be transferred to boron. So this is just similar to what we have learned for a coordinate bond. Then when we have a lone pair of electrons for one of the atoms and the other wants to it is just going to give its two electrons, share it with this atom, and as a result what we will be having is the completion of the octet, right? So this is just similar to that now, but only difference is that here already a bond between boron and fluorine is formed. So this is one bond which is already formed, but now this fluorine right? So this is saying that yes, you are my friend, my dear boron. You have helped me complete my octet. So what I can do is I can share my two more electrons with you so that your octet also gets complete, right? So this is a love from fluorine, that it is sharing this lone pair of electrons also with boron. So what is happening over here? What is happening is now there is a bond formed between boron and fluorine, right? So this is going to be what bond now? Because one bond formed is always a sigma bond. So if a second bond is formed, this is going to be what bond? It is going to be a pi bond. And it is a pi bond between the 2p orbital of boron and a 2p orbital of fluorine. So what we will be calling this as a 2p pi 2p pi bond that is being formed. And this is what we actually call as back bonding. Okay, so a bond is formed by the sharing of this lone pair or a transfer of this lone pair of the electrons from fluorine to the boron atom, this which had empty orbital. This is what we call as back bonding, right? So already a bond formed and now a back bond is being formed by the sharing of this lone pair of electrons from fluorine to boron. Perfect, I think. No confusion over here. Now the next thing is that this is the bond which is being formed, but there is also a possibility, because there is going to be the other atoms of fluorine also, which are going to have a orientation which is going to be similar to that of boron, right? So it is going to be, if this is the bond first form, this fluorine also, this is going to have its orbital like this, because all of them, they are in the equatorial plane. So it can be a bond between this also, and similarly if I have this also, so this is also going to form a bond. So what we will be seeing is we have three resonating structures for the BF3 molecule where back bonding is going to occur. So as a result, what is happening is what? That we have three resonating structures and we have a resonance hybrid where the pi bond is going to be delocalized over the whole molecule, right? So the molecule as such is going to have a partial double bond character for all the three bonds, right? So what have you learned over here is that there is going to be a boron atom which has an empty orbital, a fluorine atom which has lone pair of electrons. It is a transfer of these electrons to the boron so that its octet is getting complete. As a result, it is a partial double bond character which is going to be imparted, and when it is going to be a partial double bond character which is going to be imparted, well, the bond length is going to decrease and the bond order is going to increase, right? So when the double bond character increases, the orbitals, there is more overlapping, they're coming closer to each other, so the bond length is going to decrease. And similarly, the bond order, more is going to be the number of bonds, more is going to be the bond order, so bond order is also going to increase over here. So these are what we will be learning more further. But now, if you have understood this one thing, let us now put all this data into the slides, into words, so that you have a complete understanding of what we have learned so far. So what is back bonding? Well, back bonding is the phenomenon involving the transfer of lone pair from a fully filled shell to an unfilled shell of the adjacent bonded atoms. So what are we going to see? It is going to be a possible phenomenon which is between the atoms in a compound. In one atom has a lone pair of electrons and the other, this has a vacant orbital placed adjacent to each other. So the orientation of these orbitals also has to be similar, right? The next is that consequently, as a result, when the sharing of electrons is going to take place, the bonding which is going to be formed is going to acquire a partial double bond character, because already one bond was formed between the atoms, right? So the boron fluorine, there was already a sigma bond formed, and this was the second bond that which was being formed by the transfer of this lone pair of electrons to the empty orbital of boron, right?
So back bonding, this is going to result therefore in the decrease in the bond length and increase in the bond order. And generally back bonding, this is going to increase the stability because it is going to help complete the octet. So boron, this had 6 electrons, now it has 8 electrons because of back bonding. So there is going to be an increased stability of the BF3 molecule. It also is going to affect other properties of the molecules like hybridization and dipole moment. So we will be learning in detail about these when we are going to see further examples as well. And this can also be visualized as a type of resonance. So you saw the resonance hybrid from the various resonating structures. So this can be also seen as a type of resonance. So this is going to be a kind of pi bonding. So a bond which is formed after the formation of a sigma bond. But what you have learned so far about the pi bonding was when there was the overlapping of the orbitals which were at 90° to the internuclear axis, but they consisted of one electron each. So it was a sharing of the electrons. Now you are learning about a pi bonding which is taking place by the sharing of electrons. That is going to be a lone pair for one of the atoms and the other orbital is going to be empty, but it is going to be a pi bonding because it is formed as the second bond, never as the first bond. And generally the donor atoms which are going to donate the lone pair of electrons, these are going to be the second period elements like fluorine, oxygen, nitrogen and carbon. And when I'm telling you this, I will be discussing in detail lot many examples where we will be having fluorine as the donor atom, oxygen as the donor atom, nitrogen as well as carbon. So we will be taking lot many examples for you people so that you have a thorough understanding, because this is a very important concept. So next, sometimes we will be seeing that chlorine, bromine, iodine, phosphorus and sulfur, they also act as donor atoms, but this is going to be a rare phenomena. Some special conditions that we will be seeing when these also, they are going to act as the donor atoms. The bond angle, please do remember, of the molecule, this may or may not increase, but it is never going to decrease. So this again, when I will be talking about the examples, I will be showing you the various bond angles for the molecules. So just remember for now that the bond angles, they may or may not increase, but they are never going to decrease.
So now let us learn the proof of back bonding in the BF3 molecule. How actually do we tell that BF3 is having back bonding? Why just cannot we assume this just to be a limitation of the Lewis theory and move on? Right? So we have actually some evidence which is telling us that this is a stable molecule because of the back bonding. So the first proof that is going to be is for the boron fluorine bond length. So theoretically, if this is a single bond, the value this should have come up to 1.5 Armstrong, but actually what we find is that the bond length value is 1.30 Armstrong. So this means is that the bond length has decreased. So bond length has decreased. This means that the overlapping between the atoms has increased. Right. So we come to know from this values that the value is less than that of a single bond, but more than that of a double bond. So it is a actually partial double bond character, this BF bond which has. And while you are learning these proofs, you are actually learning applications of back bonding also. So the first application being that due to back bonding, the bond length is decreasing. Right. So the next we have is the bond order. So the bond order, again, for a single bond, it should have been, the value should have been 1, but what we find actually is 1.33. So a higher bond order, which is going to again mean that it is a lesser bond length, and lesser bond length means more of an overlapping. So this is again a partial double bond character, which the bond order is also telling us. The next thing is going to be bond enthalpy or the bond dissociation energy. Okay, so what is bond enthalpy or bond dissociation energy? It is the amount of energy which is required to break 1 mole of bonds. So more is going to be the strength of the bond, more is going to be the energy required to break the bond. Okay, so now what we have is, and this can be asked in the examination also, so be very attentive and understand this question. Okay, so the question that would be asked to you will be that in the case of the CF4 molecule, the bond dissociation energy for the CF bond is 515 kilojoule per mole, whereas in the BF3 molecule, the bond dissociation energy value is 646 kilojoule per mole for the BF bond. Explain. Okay, so now first of all, you should understand what is a normal trend for the bond dissociation energy values, right? So you all know that in the periodic table, boron is towards the left and then is going to be carbon. So as we move from left to right in the periodic table, the size of the atoms, they decrease, right? So boron, this is going to have a larger size as compared to the carbon atom. So therefore, the carbon atom, if it is this is smaller and fluorine is same in both the cases, so the bond length should be less for the CF bond than with the PF bond, right? And when the bond length is less, therefore, it is this bond which should require more energy to break this bond, right? Because the shorter bond, if you imagine you have some sticks with you, if you have to break a big stick, you will require less energy, but if you have to break a smaller stick, then you're going to require more energy. Okay, so similarly, when we have a shorter bond length, the energy required to break that bond is going to be more. But what we find is just the opposite of it. The CF bond length is shorter, but the should have been shorter theoretically. So this is requiring a lesser energy than in the case of the BF molecule, right? So the BF bond, sorry. So how do we explain this? Well, we explain this on the basis of back bonding. In the case of the CF4 molecule, carbon is forming 4 bonds. It is sp3 hybridized. So there is going to be no vacant orbital for carbon in which it can accept the lone pair from the fluorine atom. But in the case of BF3, now you know very well that back bonding can take place and back bonding has taken place. So what we have is the bond length, which should have been this much, but now it is less, right? So because it is less, so the energy required to break the bonds is going to be more, and hence we have the higher bond enthalpy or the higher bond dissociation energy values. So I hope this is clear. It is because of the back bonding in BF3 that we have a higher bond enthalpy value for the BF bond as compared to the CF bond in the CF4 molecule. This is a question which is frequently asked. That is why I was playing a lot of stress on this question. Now the next thing is the order of the lowest acid character of the boron halide molecules. Again, this is going to be one question which is going to be frequently asked in the examinations. So what do we have a lowest acid as? A lowest acid is going to be an molecule or an atom which is going to accept a lone pair of electrons easily from another atom or another molecule, right? So lowest acid character depends upon the easy acceptance of the lone pair of electrons. And in case of the boron halides, all of these, now you understand that boron is going to be electron deficient, right? Boron trihalide is what I'm talking about. So it is going to be electron deficient, and if it is a fluorine, chlorine, bromine or an iodine, all of them, they have lone pair of electrons which they can readily give to boron, right? So now what should be the lowest acid character for these molecules? Well, if you see over here, if I write this as boron, I just cannot write this very well, but I hope you will be able to understand what I'm writing. So it is boron, then the two fluorines, and this is the third fluorine. So this is the BF3 molecule. So when we have the BF3 molecule, fluorine is going to be the most electronegative when we compare all of the halogens, right? So if it is more electronegative, so it is going to pull the electron pair towards itself. When it pulls the electron pair towards itself, the boron atom electron deficiency, this increases further. This increases further. So this means that this should have the maximum uh, affinity for the upcoming lone pair of electrons. So this should be having, in other words, the maximum lowest acid character, because fluorine is the most electronegative and the rest of them, they are going to be slow and steadily as we go down the group, the electronegativity values, they are going to decrease. So what should have been the order? The order should have been BF3, maximum lowest acid character, and down the group the lowest acid character, that should be decreasing. But what we find is it is actually the opposite of this. What we see as the lowest acid character is just the opposite of this. And we explain this opposite lowest character on the basis of back bonding, right? So because of back bonding, and if we consider the type of back bonding that is going to take place in all of them, it is going to be a 2p pi 2p pi for boron and fluorine. It is going to be a 2p pi for boron and 3p pi for chlorine, right? And then it is going to be for boron again 2p pi, but for bromine it is 4p pi, and for iodine it is going to be 5p pi. When is going to to be maximum overlapping taking place between the atomic orbitals? Well, it is going to be when they are equivalent in energy, they are similar in size. So the best back bonding is going to occur in the case of the BF3 molecule, because here we have both of the orbitals to be the 2p orbitals. So this is going to be the most effective overlapping. The strength of the back bonding is going to be the maximum. Then obviously it is going to be BCl3, where it is a 2p and a 3p orbitals. But when we consider boron bromine, it is going to be 2p pi 4p pi, and here it is still a larger size of the atomic orbitals. So obviously I hope you can understand now that the back bonding tendency decreases as we move from fluorine to iodine. So the lowest acid character is also going to be maximum for boron iodide. Okay, so this is going to have the maximum lowest acid character, and BF3, because this has become stable because of its electron deficiency of the boron being fulfilled by the fluorine atom itself. So in the molecule itself, it has got its electrons. It doesn't need any further electrons. So this is going to be the maximum stable molecule for out of these, and this is going to have the least lowest acid character. The next thing, another question. So these are actually how you can have the applications of back bonding. So I am just talking about BF3 molecule and the concepts related to it. There are going to be so many other questions which can be explained. We will try our level best to give in you the maximum what we can, and then I hope you will be able to crack any question related to back bonding that comes forth you. So the next we have is why BF4 negative, this does not show back bonding. Well, this does not show back bonding because now in the BF4 negative, it is going to be a increased covalency for boron. So now boron is no longer sp2 hybridized, it is going to be sp3 hybridized because it is forming 4 bonds. So there is going to be no available orbital for which is going to be vacant for the fluorine to transfer its electron pair, right? So there is going to be no back bonding. So there is going to be also one more thing over here that you can understand, because now this will be all single bonds, and in case of the BF3 it's a partial double bond character. So the bond length for the BF4 negative, the bond between boron and fluorine, this is going to be longer than the BF bond in the case of BF3. Okay, I hope this is clear. So now quickly I will be telling you certain more important facts, because I want to cover the theory in this topic in this lecture, and then we will be talking about the examples which will help you increase your knowledge about back bonding in the next one. So back bonding, this is also called as pi coordinate bonding, and I hope you all understand this now very well. That first bond was the sigma bond. So back bond is going to be the second bond, so it is going to be a pi bond, and it is also a coordinate bond because it is only one of the atoms which is putting in its electron pair and sharing it with the other atom. So the next is that the compounds, they can be of two types based on the type of back bonding. One type of compounds are going to be the ones in which the side atom is going to donate the electron pair to the central atom, just like what we have done for boron trifluoride. So in this, fluorine is the side atom, boron is the central atom, and it is fluorine, the side atom, which is donating its electron pair to the central atom boron. So the next type of compounds are going to be the ones in which the central atom is going to donate the electron pair to the side sources. For example, in the case of this molecule, which we call as trisilylamine, it is going to be nitrogen, which is going to donate its electron pair to silicon. So I would like to discuss more about this, but that would be in the next lecture. Just remember this over here. It is going to be nitrogen, which is going to donate its electron pair to silicon, and it is going to be a 2p pi and 3d pi back bonding. So it is going to be silicon's 3d orbital which is going to receive the electrons, and it is going to be obviously nitrogen's 2p electrons which are going to be donated. So it is going to be a type of 2p pi 3d pi back bonding. I will be talking more about this in the next lecture. Now, the important thing over here that you have to remember is going to be the conditions necessary for back bonding. So whenever you are given certain choices that you have to choose those compounds where back bonding is occurring or not. So what is going to be your criteria? So first is going to be any one atom in the pair. This should at least contain one lone pair of electron, right? And the other is going to be, and obviously that the second atom of the pair, this should have a vacant orbital as well, so as to accept that lone pair also. And the second criteria, please do remember this is going to be very important, that at least one of the atom, this belongs to the second period and the other belongs to the second or the third period. For example, in BF3, both of the atoms, boron and fluorine, they are second period elements. But in case of trisilylamine, we have nitrogen to be of the second period and silicon to be of the third period. So do remember this criteria while you are choosing which of the molecules are going to show back bonding. The next thing is going to be the strength of the back bonding. So strength of the back bonding is going to be directly proportional to the size of the atom. So I have already told you this also, that an effective overlap is going to take place when the orbitals, they are going to be of a similar orientation, similar size, and similar sizes of the atoms. Okay, so for that you can understand. So we have 2p 2p pi back bonding to be the strongest, then 2p 3p, and then 2p 3d. And this is going to be again in the terms of the orbital size. I hope you can remember. So if you have to, for example, compare the back bonding strength in the case of BF3, BCl3 and PF3, BF3 is going to have the strongest back bond, whereas in case of the PF3 molecule, it is going to be the weakest. Right? So I hope these things, they are clear to you, and I am going to come back with the next lecture on a detailed examples of back bonding. So that would be all for this lecture, and I've already told you what I'm going to teach you in the next lecture. So please, if you've liked the lecture, do click on the like link. Also do click on the subscribe link and do subscribe to the channel and click on the bell icon so that you get the notification the moment the lecture on the examples of back bonding is ready. So see you again. Have a nice day. God bless you.